Welcome to the first podcast of Fool's Or, where we explore computer architecture on the transistor level. In this episode, we're going to be building our own CPU from scratch in a digital logic simulation. So enjoy the next hour of computer architecture. Okay, so welcome to this episode of Fool's Or, and this is going to be a really long episode. We're going to make a computer, and I'm going to show you all step by step how to set up all the logic gates properly in order to make this computer. So we are in the digital logic simulation by Sebastian Lague. I think that's how you say his name. And we are just going to go right into it. So new project, going to call it Fool's Or. And then first thing is we only have one gate right now, which is the NAND gate. And I'm going to show you how it works real quick. So when both the inputs are off, the output is on. But if both the inputs are on, the output is off. And this one gate can make a whole computer by itself. And I mean, that's how the simulation works, and that's exactly what we're about to do. But all you need is this one gate, which is kind of cool. So this is the NAND gate. So if we remove one of these and then hook up both, or one input to both of the inputs of the NAND gate, we get a NOT gate. So we're going to save that. And if you don't want to watch this full video, because it's probably going to be pretty long, you can just follow each of my series that I have in a playlist about how to make a computer. But this is just going to be one full episode. So, and we're not going to make this optimal. I'm just going to make this so I can explain it the best way possible. So if we have a NAND gate, wait. I don't think I saved it, my bad. There we go. So we have a NAND and a NOT. Then we make an AND gate. So if both the inputs are on, the output is on, which is going to be useful. Now, if we NOT both the inputs first, then go into an AND gate, we get an OR gate. So the output turns on if either or both the inputs are on. And then we need to make a NOR gate too. Just like the NAND gate, we need to make the opposite of the OR gate. Just like that, we got an OR gate. And then now we got to go into these two different gates called the XOR gate, which is what the name Fool's Or is named after. So if we take 4 NANDs and go into this configuration right here, we get a special type of gate. And now the output is on if either or of the inputs are on, but not if both. If both of the inputs are on, the output is off. And then there's multiple ways to make this gate, but this is the way that I remember how to make it, and it's called an XOR gate. And then like the other ones, we need to make an XNOR gate. So just the inverse of the XOR gate. So these 7 gates are all the gates that are considered primary gates, you can say, and they're used to make computers. So a computer is defined as an electronic device for storing and processing data, typically in binary form, and it has instructions given to it in order to do the computation. So that's exactly what we're going to do. And processing data is a key word. So a way computers can process data is by adding and subtracting. So we're going to make the adder first. And then, so the way you make an adder is you're going to make something called a half adder first. Oh, wait. Yeah, there we go. So now we can name these inputs. There, make it a little easier. That's good. So this is a half adder right here. So 1 plus 0 is 1. 1 plus 1 is 2. So in binary, you can watch my actual adder video for more clarification. But in our base 10 system, when we add numbers and the number goes over 10, we have to carry the 1. But in binary, if the number goes over 1, we have to carry the 1. So that's exactly what we're doing here. So 1 plus 1 gives us 2, which would light up this gate so we can carry the output kind of going forward. So this is called a half adder. So if we have 2 half adders and an OR gate, we can make a full adder. I'll put carry. And this is what we call a full adder right here. So 1 plus 1 is 2. And then this is the other carry input, so we can chain these together. Because just like base 10 system, if you add 2 numbers, your carry 10 can make a third column in the top right row. So that's what this carry input is right here. So we have to do it like this. And it works because 1 plus 1 is 2. And then plus 1 is 3, which gives us the answer right here. So this is called a full adder. So if we chain these together, which this is going to be a 4-bit CPU also, we can get a full adder. So this is it. So let's see if it works real quick. We'll have 2 plus 2. Oh, I gotta carry these together. My bad, guys. Here we go. So 2 plus 2 is 4, which works. 2 plus 3 is 5. We can go with 6 plus 6 is 12. So it looks like it does work. So this is our adder, you can say. So we'll save the chip real quick. 4-bit adder. There we go. So now we need to make the full ALU, which would also involve a subtraction part. So actually, we're just going to manipulate this adder to make the full ALU. Or actually, we're not. I changed my mind again because I don't really feel like redoing this all. So the way we make a subtractor, and you can look at my subtraction video too for more clarification. But all we need to do is put these XOR gates into the first 4 inputs, just like this. Then we need a button to turn on subtraction mode. And then we got to hook it up in a special way. So let me wire this up real quick. There we go. So we have the adder 2. And then if we put the subtractor on, it kind of inverts everything. Oh wait, I forgot this one crucial part. I'm sorry. Let me save this real quick. So if we go back to the this, we need to make an input. Right here. So we don't have to use this carry input when we're adding, because you can't carry anything on the first column of when you're adding, just like base 10. But subtracting, it's crucial because it actually does a little trick for us. So now, when we turn subtract mode on, we get the carry output becomes high when it equals 0. So this is also kind of a 0 output, and it's also the carry output. So I guess we can call it both, which is good. So if the two numbers are equal to each other, and if they're equal and we subtract them, it gives us 0, we have a flag triggered right here that we can send to other parts of the CPU. So, but it still works. We can still add. We've subtract mode on. So 2 minus 0 is 2. 2 minus 2 is off. 2 minus 1 is 1. And so it works. And again, if you want more detailed on how exactly this mechanism works, I have a full subtraction video. But this right here, we're just kind of like trying to speed run how to make a computer. So it's not really too important right now. But this is our ALU. So now we need to make a memory storage device for our ALU. So this is the most basic way to store information, and it's just called an SR latch. So notice how the outputs are going back into the inputs. So it can almost remember what state it's in, which is kind of cool. So I mean, we can have well, it's called SR latch reset and reset. So I'll have this as reset, and then this is set. Since when we turn this one on, it makes the top output go high. And we'll call this one Q, and this one will be negative Q. since it's the inverse of what Q is, which could come in handy a little bit later. I'm just going to call it SR. So we have an SR latch, the two outputs, and then we add these two AND gates, and we invert one of them. We get a data latch. So if the store signal is high, we store the output into Q. Just like this, and that's kind of it. So this kind of simplifies the SR latch, so we can store data, but we can only store it if the store signal is high, just like this. So say the chip is a D latch. So we have 4 of these. We can kind of make a D latch register, which can come in handy, but sometimes we need like a clock pulse D latch, and I'll show that in a second. But right now we're just gonna make a D latch register. And all we care about is Q, so it doesn't really matter. Okay, so but the problem with the D latch is that if the store signal is high, we store data. So if we connect the output up to our ALU and we feed the ALU new information and the store signal is high, it's just gonna like kind of keep cycling through and through. So I don't know if that made sense, but I can show this real quick since it's pretty easy. Oh wait, my bad. So I'm just gonna use this NOT gate to make this high. If this is high, and we go back into our ALU, it's going to glitch out. So we need to make a special type of gate, but I'm trying to make this fast so I can show y'all. See? And then it glitches out, kind of adding it together. So we need to make a way where it will only store one number for a high signal. Then we have to wait for a next clock pulse to store another number. So we need almost a clock sensitive register, which that's what I'm calling it. Because this one is not clock sensitive. We would almost need to make a pulse like really quickly in order to store the data at the correct moment, which is impossible in the simulation since we don't have pulses, you can say. At least pulses that work. So we're going to make a clock one, in which we can do that with pure logic gates, thank goodness. So, oh, my bad. So we can do it with 2 D latches actually. So data, and then clock. And this is called a master-slave D-latch. And it's called that because this one controls this one. And so the master and the slave, I guess you can say. But that's the technique we're using. And we'll use this in another area too in the future. So we have the data is going to go to here. There we go. See? And so when the clock pulses, every clock pulse, it changes the data. Let's wire it a little differently. So it goes on the leading edge instead of the falling edge. And that's simple. We just got to reverse these two. So now it does it on the leading edge instead of the falling edge of the clock, which is perfect. This is exactly what we want. So we're going to call this a master-slave D-latch. And then if we do the same technique we did with the normal one, just get 4 of these, we can make a little register with it. And we can call this a clock one. So let's see if it works real quick. Yep, we're good. So we're gonna call this master slave D-latch register. There we go. So now if we have the ALU and then our new and improved register, in which this is gonna be the CPU now. Oh, I always do this, man. And now we can add it relatively easily just by keep pulsing the clock. And we're just going to add by 1. So this works really well, actually. So we can kind of start building our CPU. And the design I'm going to use, or the architecture, is called an accumulator CPU. And it's called that because this main register right here is called our accumulator. So, and it's going to store the output and feed it back into the input. This right here is the main focus of this architecture that we are using. And so we can use a normal register right here since it doesn't need to be clock sensitive. And I know I didn't say optimization, but this does help out on transistor count and complexity of the circuit, as you've seen. And then we can add a little SR latch right here. So if it's on, this will make subtract mode high and vice versa. So I can label this so versus, and that's going to come in handy in the future. So cool. Now we need to make a control unit. So we have so many modules and so many things we can do now. We can either store into this register, we can store into the accumulator, we can make the ALU add or subtract, and oh yeah, this is called the instruction register too. So we can label it. Kind of forgot the name for a second. Instruct. So we have so many things we can do. We need a control unit that can control each of these components separately, and we can put it in the code which one we want to activate. So I'm just going to save this right here, and this will be our CPU. And a control unit is pretty simple to make. You just need a whole bunch of AND gates. So we're going to make a 4 AND gate thing real quick, because that's just going to help us when making the control unit. Wait, my bad. So now the output is only on if all of the AND gates are on. So we're going to call this a 4 AND. So we take 5 of these, and we're going to have 5 main instructions, or yeah, we'll have 5 main instructions. And all we need to do is make a little decoder. So it's going to decode a 4-bit binary number into individual outputs. So as you can see, if 1 is the input, we get the first one on, just like that. And we're going to call these different things because they're going to do different things in our computer. So this one's going to be accumulator store. This one's going to be instruction register store. Add. Subtract. And display. And I'll show you what display is. It's super simple, so that's why I didn't go over it. So if we have 2, then we're going to need this output. And it's like this for all of them. So it gets kind of repetitive and it uses a lot of wires, but it is crucial in being able to decide what we want to do next. And there we go. It looks like it works well. Cool. So this is our control unit. And then if we go back to our CPU, we can just easily add it in right here. And then we can also add in our display unit right here. So the display unit is just going to save what the output was so we can display the information to the user. So easy. Subtract. Let's go with this one. So we're just going to have to hook these up to these little inputs right here. And then we have this SR latch so it can kind of remember it's in subtract mode for multiple clock cycles in case we just want to keep subtracting. Okay, so cool. We made some progress with this. Now all we need is our instructions, so our code, and we need to make a program counter so we know what clock cycle we're on. So let's make the program counter real quick. So this is going to be made using a JK flip-flop, and we're going to use the same master-slave technique that we've been using. So this is a pretty complex little circuit. It's going to use 8 NAND gates. And it's more like a T flip-flop than a JK flip-flop because every clock cycle we're going to add 1 or flip-flop the number, and we won't have any other inputs to really affect that because the CPU won't have the jump ability, just to keep things simple since we're already at 32 minutes in this video, and that's kind of absurd. But okay, so a lot is happening right here. It's kind of these two D latches, you can say, together in series. And this is the master, this is the slave, because this one controls this one, just like we said before. But a unique thing is that the outputs on the far NAND gates go back to the inputs on the first NAND gates. And this allows us to give us this toggle cycle, just like this, which is very useful in adding numbers by one instead of using a full ALU and register combo, which can be a little too much sometimes. So I'm going to call this a T flip-flop. And then if we chain these together, we can get a little adder. You see, and all we're doing is adding by one. And this is going to be our program counter. Yeah, we saved it. Now we go back to our CPU, which is right here. And we can add this all the way over here. And we can also add the clock module too, which is a built-in module. Okay, so now we're going to need to build another decoder to decode the program counter. And we are going to need to build an instruction set. And then we are done with the computer. So we're just going to build going to build our decoder first, and we're just going to kind of, since the control unit is a decoder, we're just going to use it again. But I want to make a new module just to keep things a little neat. And we'll have 5, so we're only going to have 5 clock cycles or 5 instructions just to keep things again simple. We'll call it a 4 to 5 decoder. So we go back to the CPU, and then we can add this decoder just to the program counter. And now we can choose which instruction set we want to be visible. So I'm going to save this, and now we're going to make our instructions called the opcode. And then we're going to have to use something called a tri-state buffer. So we're going to use a bus, an instruction bus for this. And the buffer allows us to write on the bus without corrupting the data from other units. So we need to make some like memory type thing with it. And then, yeah, we need more of these. 8. We need 8. So So this right here just allows us to put this 8-bit thing back into 1, just to make life a little easier, because we are using an 8 opcode where the bottom 4 is for numbers, so we can store in the register, and the top 4 is for the control unit, so we know what to control. And we do need our enable pin, so we can enable these buffers to output their data. So the way this works, real quick, is you can see these are black and these are gray. The gray represents a 0, and the black represents neither a 0 or a 1. So we display something on here. The buffer prevents it from being activated until we enable the enable pin, and then it can be activated. So pretty straightforward. I'm going to call this an opcode chip. So if you go back to our CPU, right, 1, 2, 3. And then we can make an 8-pin bus. So right here, there we go. Just like that, and then we can connect all of these straight up to the bus. Move this a little bit. And then we can hook this up back to the program counter, so we can enable each one at different times in the clock cycle. And that's what the whole use case of this was. Everything's coming back to itself. There we go. Oh, cool. And then if I play the clock, see, we just run through the cycle. And it does display all 4 bits, so we can have theoretically 16 of these, but for this clock cycle we only have 5, so it's going to be a little short on the timing of some of these. So now we have to split up this to the control unit and then some to the instruction register. So all we need to do is we need a splitter, right? So 8 to 1, we need 2 of these. And these are going to be the top 8. And then these are going to be the bottom 8s. So cool. I mean, this is the CPU. Let's save it. What, that was about 45 minutes. But we made a permit. We did it. We actually made a primitive CPU. So that's kind of cool. Yeah, so let's save. So the instructions is going to be 2. So we can see we save that. And then we're going to put this into subtract mode real quick, which is 1, 2, 3, 4. 4. We are in subtract mode, so that's cool. The number is 112. What? 13. 13. We're going to save it, right? Yes. And then we're going to save the accumulator real quick. So now we're storing 0 in that, and then we can store, yeah, so we kind of like just reset everything. Display is what? 1, 2, 3, 4, 5. Display is 5. So yeah, everything's reset now. I'm gonna get out of this so we're not like kind of manipulating it. Okay, and now we're just gonna do a very simple program, which we're going to store 5 into the instruction register, and then we're going to store it into the accumulator. We're going to go into add mode, which is what, 1, 2, 3, and then we're going to store 2 into the instruction register, and then we're going to display the data, which is what, 1, 2, 3, 4. I always forget these numbers. Right. And then it's just going to kind of keep repeat doing this. But what is this? So we have 5 plus 2. 5 plus 2 should be 7. Should be 7. So we should see 7. Oh, that was kind of freaky. Which we might manually do this by hand. We do have a little glitch in this app. I don't know why it exists, but it does. Where sometimes you have to just manually do the clock for it to work. So we have we need to store that first. Yeah, so we store this in the instruction register, and then we store. Fuck. My bad. Yeah, let's wipe everything clean real quick. Okay, so yeah, let's redo this code. I kind of messed it up a little bit, but that's all right. That's all right. So 5, there we go. Actually, first we're just gonna put this on add mode, and then we're gonna store 5, and then we're gonna store 5 into the accumulator, and then we're going to store 2 back onto the this, and then we're going to display the data. Okay, simple. So now we're going to add mode. Why did this store? That's interesting. Interesting that we stored this number, but it's fine. But yeah, so we did it. I don't know why it didn't. This is weird. This is weird as hell, man. Okay, yeah. Now we store 5, and then we have 5 coming out of this register, correct? Yeah. So we save that. Then we have 2. Which is 10. Oh, we did have 7. It just didn't display 7 for some reason. But yeah, this is it works. It does work. So we can get it to do what we want. And then if we add 2 to this, we can see what we get. There you go. So cool. It does work. And yeah, that's it. This is how to make a computer in under an hour. Long video, but this is all the basics. So thank you for watching. I hope that you watched this whole video. If you did, please leave a comment and let me know you did, because that's awesome. But if you have any questions about this, please let me know. All the glitches, you have to trust me on this one. All the glitches that we've seen was part of the simulation, not part of the computer. And in the future, we're going to make a computer out of pure transistors in simulation and in real life, like these baby computers I have right here. But that's it for this video. Thank you for watching. Please subscribe. The more subscribers we get, the better my life becomes, and the more I can focus on doing this content, because no one else is doing this on YouTube. It's only me. But it's all my begging out the way, and I'll see y'all later.